chapter 12. We are looking into all of the sections. And standard setup for the exam, 10 questions, replacement problem, hour and 25 minutes for the exam, and then the lecture right after. The class is 2 hours, 45 minutes long, so we'll have time to take care of 13.4. The most important stuff. So technically, if you just look at the titles, you know what's on the exam. We had 9 sections, so it's fairly easy to come up with 10 questions. You can expect a problem per section, and then we're going to double up on something. So planes and surfaces. Probably that's what's going to be doubled up, because there's equation of the plane and how to find the plane, and then surfaces. Remember the multiple choice that I was mentioning to identify the surface with the equation, or equation is given and then 4 pictures to kind of figure out what's what. If any of the multiple choice questions pop up, it is either 5 points for correct answer or 2 points for wrong answer. So that's the one that you don't get 0. It's 2 points free at least. The multiple choice questions, we can have at most, I would say, on a test 2 questions, right, for 10 points. The rest is all going to be partial credit, obviously open-ended questions. So without me writing that long list, there is no need to write a long list. I will just go with, you know what sections and what titles are. So I will just write out some concepts that you should definitely spend time with, because those are extremely important. So planes, and then tangent planes, and then limit D and E. Remember, to find 2 paths or infinitely many paths. Partial derivative. And then we have the chain rule. And for the chain rule, I'm going to emphasize the tree, because if you are able to set up the tree, you will be able to finish up everything else, to get the equation and do it. Directional derivatives and gradient. See, I'm not going to put the gradient problem on it, because gradient shows up all over the place. The tangent plane has the gradient. The Lagrange has the gradient. So you are technically looking into directional derivative question from that section. Tangent plane, I already said that. The linear approximation, if it's there, you just compute the tangent plane. We have a min-max problems. Min, max, saddle. And I'm inclined to put the 2D domain on that one. And then Lagrange. Also the 2D input problem, so that you are not chasing, 4 variable rather than just do 3 variable. It's evil enough. You're welcome. But I did. You want 3D? Okay. Then say something. So that's the list. Any questions or concerns? Just questions. Don't worry about concerns. No concerns. Just questions. Any questions? Would you like to see any problems? Do you have any problems that you? Matt has problems. Yes, Matt. Lagrange. Which? Yeah, you need to give me the problem. Not concept, problem.
Chapter 12.8.
12.8.
Number whatever min and max are.
Lagrange.
12.9. Lagrange.
And then there's another one, Laplace.
Laplace is in differential equations. Laplace transforms. Oh yes, yes. What's the problem number, guys? 23.
What's your problem?
All right.
Yeah, let's go.
Hi. Problem 23 from section 12.8 on min max / saddle. We have the function fxy given as, no coughing, x to the 4 plus 2y squared minus 4xy. And we would like to know min, max, saddle, any critical points. We find partial derivatives. So 4x cubed minus 4y. Have to set that equal to 0. And then fy is equal to 4y minus 4x equal to 0. And then we have to solve this system. Observe that both of these have 4y. So we can solve the top equation where the 4y is equal to 4x cubed. And the bottom one, 4y, is equal to 4x. And now we equal them. We get that, well, we could have canceled all the 4's. Cancel all the 4's. So we have y equals x cubed, y equals x. So x cubed equals to x. And now, how do we solve this equation? I'm just interested. What's the proper way to solve this equation? Yes? No. Move the x, exactly. If you divide by x, you are losing a solution. You are not allowed to divide. You have to subtract x and then factor. So this is x cubed minus x equals 0. And then when you factor out x, you get x squared minus 1 equal to 0. And then you have x, x plus 1, x minus 1 equal to 0, which gives you 3x solutions. X is 0, x is minus 1, and x is 1. If you divided by x, you would lose the solution 0. Yep. So now, and we also have that y equals to x equation on top of what we have. So we have 3 points, 0, 0, negative 1, negative 1, and 1, 1, because of the equation and that stuff, right? X equals y. So now we're good to go. We have 3 points. All we need to do is to figure out the second derivative test and find what they are: min, max, saddle point, or the test is inconclusive. Yes. Critical points. Yes. So now we need fxx. Fxx is 12x squared. Fyy is 4, and fxy is -4. We create that function d, function of second derivatives, thank you, which is the determinant of the matrix, but that's linear algebra. So d, which is the reason why it's capital D, is determinant, but d is equal to 12x squared times 4 minus -4 squared, which is 48x squared plus 16, minus 16. So now we are going to test the first point, which is 0, 0. So d is negative. For -1, -1, d is positive. And for 1, 1, d is also positive. Oops. So we have the first, when you compute, this is your d equation. So when you plug in 0, it's -16. -16 is less than 0, so d less than 0. You compute everything 1. Now, what did we memorize from the thing? If d is less than 0, is saddle. You have to memorize that, guys. That's the bottom line. You have to memorize that one. So now you have that. Now, when d is larger than 0, you have to check fxx. Very good. And if fxx is bigger than 0, it's a minimum. If it's less than 0, it's a maximum. So now fxx is 12x squared. That's going to be larger than 0 in both cases. So min and a min. So this was like a perfect size exam question, I would say, where you guys can show off your math skills in 12-8 without being too much concerned with crazy calculations and equations and so on. Yes, Matt? What do you mean 1, 1? D is larger than 0, fxx is larger than 0, it's a minimum by definition. No, fxx squares 1, right? So either one you put there, it's going to be positive. So yeah. Yes. Now, one more thing that I need to say, guys. These are only x and y values. You don't know until you take this into original equation what the z value is for the height, right? Remember that for the you have the function f of xy, which is your z, so z equals the function, and you need to plug these numbers in to obtain the z value, and you add that here at the end, and you would say it's a minimum, and you see what the z values are. So this does not display z values. This is just the points in the domain at which those min, max, saddle occur. But to find where they actually are in space, you still have to compute the z value using these as inputs, and that would be the third there for the spatial point, right? Yes. So if I want to describe this light, I put a dot in the domain, which is the floor. And that's the location where the light is. But that's not the spatial location where it is, because I would have to have these coordinates on the floor, which is the domain, which is those guys, and then comma 10 feet out, right? So comma 10 to describe where the actual light is. So these points are just domain locations, and then to know the height, you would have to compute the z value. Yes, sir?
Okay, so on the test, you said in 2D, but you keep going and like find the z value and figure out if it's a cell and
You finish early, what you're gonna do is just compute that stuff. But, yeah. You wanna know. You nosy, you wanna know. Yes. No. Since I know you're not going, you have time. Are there any other questions that you might be interested in? Yes?
Lagrange, I have one.
For Lagrange? Is that your question as well? We have to, yes. Which one? Page and the number. Oh, you're not ready?
I didn't come prepared.
Lagrange it is then.
Alright, f of xy is equal to
F?
from the study plan on alpha. Alright, if f of xy is equal to 3xy plus 4x plus 4y subject to x squared y squared equals 25.
Equals to?
25. 25.
There we go.
I want to know what the max is.
So this is Lagrange. Well, if it's a word problem, you have to find one. If it's like this, a word problem is more likely because it's application. All right. Let's do Lagrange. So we have our function f. This is our function g. So function g is x squared y squared minus 25 and equal to 0. So del f equals to this is a vector lambda del g. And we find vectors of partial derivatives. So partial of x, 3y plus 4, partial of y, 3x plus 4, equals to lambda, over here g, partial in respect to x is 2xy squared, it's all symmetric, and then 2yx squared. This gives us our two equations. 3y plus 4 is equal to 2 lambda xy squared, and then 3x plus 4 is equal to 2 lambda yx squared, and we have x squared y squared equals 25. This over here is our system. We have x, y, and lambda, three unknowns. Now for symmetric systems like this, where x is interchangeable with y, we can simply immediately conclude that x is equal to y. Because if you look at the two equations, they are identical. right? Look at equation 1 and equation 2. So that implies that x is equal to y. You would probably solve for 2 lambda in each equation, and then set 2 equations to each other, and a whole bunch of stuff will cancel. And
Would it be wrong to solve for y?
anything you can do. These are nonlinear systems. There is no set procedure. It's like UFC. You just have to go in and dance. Try to survive, you know. Or when you first time swim, just make sure you. That's all it is. Not a problem swimming, right? Swimming, I don't know. You get born, you get thrown in the water.
I told him how to drown first. So he's not afraid of drowning.
That's
I
not.
told him,
Good game, good game. Oh, they're done for the day. So let's solve this now. So you would set 2 lambda and 2 lambda equal to everything else. You would equal those two, and it would work out from there. So now, because x is equal to y, we actually have x to the 4th is equal to 25, which is x equals to plus minus root 5, which is y equals to plus minus root 5, because they're the same. And we have our answers, and then we get to test which combination. So root 5, root 5, root 5, negative root 5, negative root 5, and root 5, and negative root 5, negative root 5. Plug them all in the original function, figure out which one is the max, which one is the min. Some of them might work out negative, some positive, so whatever is the highest value is the one that wins. Fair? Let's compute the first one. So it's, what was that, 3 root 5 minus 4 root 5 minus 4 root 5. Is that true? Original equation. No, it was plus and plus.
How are you finding which one's max?
You plug them in a function. You plug each one of these points in a function.
Do what you did to like step through the test and the rules?
No, not the rules. You just plug these values in the original function and take a look which one has the highest z value. So this is 5, 15 plus 8 root 5. The next point would be 3 root 5 negative root 5 plus 4 root 5 minus 4 root 5. These guys cancel. You get negative 15. So you see how the second one, because it's symmetric, the third one will be the same, negative 15, and at the end the other one will be 15 minus 8. Root 5. So clearly our max is at root 5, root 5. Did this make sense? I hope it did. It's a perfect length for the test. Good size. Yes. Yes, in the function f of xy, find the z, because fxy is z, right? So the highest of all z's is the maximum, the lowest of all z's is the absolute minimum. Farmer, boxes, the straighters field. Optimization field. Yeah. What happened?
What would it say that the able we have to find the
You want a cone? Which one? There's a book right there. So duplexes. What's the reaction time? Have you ever tried the reaction time? No. All right, here's a good word problem. Word problem.
Already committed.
problem 60.
All right. Quickly before Dave comes back, 26 on Lagrange. 12.9, problem 26. Box with minimum surface area. So the word problem says, find the rectangular box with a volume of 16 feet cubed that has minimum surface area. Find the rectangular box, which is the dimensions. Rectangular box with a volume of 16 feet cubed that has minimum surface area. So, we first draw the box. X, Y, and Z. And so find the rectangular box with a volume of the, so we know that the volume is X, Y, Z is equal to 16 feet cubed. So guys, this is your constraint equation because you have everything there, so therefore that's your G. G of X, Y, Z is xyz minus 16 equals 0. Now, it's the one that you are minimizing or maximizing, which is your objective function, which is the f. So in this case, is a surface area. So surface area, you see you have 6 rectangles there, but it's 3 pairs. So the surface area, call that S, is going to be 2xy plus 2xz plus 2yz. And you want to minimize that. So that is your f, xyz. 2xy plus 2xz plus 2yz. So now you have your volume equation, your area equation. You created the constraint equation G and the objective equation F. And now you unleash Lagrange. We have del F is equal to lambda del G. So what do we have? Partial derivatives, 2y plus 2z, comma, partial derivative in respect to y is 2x plus 2z, and partial derivative in respect to z is 2x plus 2y, is equal to lambda. Partial derivative of xyz minus 16 is going to be yz, is going to be xz, and it's going to be in terms of z, xy. There we go. So now we are going to create our 4 equations because you picked a problem with 3 input variables. So 2y plus 2z is equal to lambda yz, and then 2x plus 2z is equal to lambda xz, and 2x plus 2y is equal to lambda xy, and you still have xyz is equal to 16. So now, I would solve for lambda, because lambda is the only thing that we don't actually care about. So we can solve all 3 equations for lambda and make 2 pairs of equations eliminating all lambdas. And then we are down to system 3 by 3. So lambda from the first equation is 2y plus 2z divided by yz. Lambda from the second equation is 2x plus 2z divided by xz. And lambda from the third equation is 2x plus 2y divided by xy. And now you equal first and the second, first and the third, or whatever way you want. We get 2y plus 2z over yz is equal to 2x plus 2z over xz. And that can simplify. If you divide both sides by 2, all of the 2's drop. And if you multiply both sides by z, z's drop as well. So one of the equations that we want to have around is going to be, oh, and then you cross multiply. So it's xy plus xz is equal to xy plus yz. And then y, when you subtract on both sides, goes away, and you have xz is equal to yz, from where you get that x is equal to y. And then similarly, because all of this is symmetric in this case, you're going to get that y is equal to z and x is equal to z. So you are actually going to have x same as y, same as z, and that's going to give you a cube. Since your volume for the cube, so if it's a cube, then x cubed is equal to 16, x equals to 2 cube root of 2. Well, here, cube root of 16, 16 can be written as 8 times 2, cube root of 8 is 2, 2 cube root of 2. So dimensions are x equals y equals z equals 2 cube root of 2, and it's a cube. Cube is the special case where you get the smallest surface area for whatever constant volume you have. That's why it's so special.
Just the length.
This is the length of each side. It's not a coordinate, right? So coordinates of 0, 0, and then
So no.
Are there any questions you ever find that the book right there is yes? What you don't know, we got a calculation that x is equal to y. We're starting assuming that they're not the same. And any other requirement, if I do the same problem like the same, the only thing you do this problem for any question, or say, oh my god, right? Yeah, with the surface area function, we're going to have bottom and fly, and then you won't be able to have x y z, and therefore you need in the application, you only get one answer going on. So that's how it is managed. You can always, but then you have to check. But 90% of the time, without spectrum,
So how would you solve this no, next week. Yeah.
because access area implies I cancel all the schools because when you add those types of two, And then I multiply both sides. But there was a denominator, right? No, of course. But Following? Okay, fine. Any further questions, John? It's coming up on the All right, who's in for basketball? All right, good. Sharif, basketball? We'll have to come up with a time. Not obviously, not this weekend because of the test, but. I haven't played a long time. Do I? You play? Okay. The people over there. You gonna bail or not? It's like, yeah, and then you're gonna bail, right?
When?
We'll talk about when. We'll just get the people interested. Basketball? Good.
Can we play volleyball? I love volleyball.
Yeah, but we have nowhere to play. Unless we go to the park, but now it's you got to pay. Next problem is a chain rule problem. What's the page? Oh, it's Larson book. Okay, so what's the question?
V sub S, V sub T, Z sub S, and Z sub T, where Z equals E raised to X plus T. X is equal to ST, and Y equals S plus.
So E is the X plus Y, right?
Yeah, that's what I said, X plus Y.
No, you said X plus T. We can roll the stream. Roll the stream.
We can replay it later.
Yes. And if you're wrong, I get to style your hair. If I'm wrong, you get okay. It's part of styling. Sorry. So this is going to start at Z, which has two variables x and y, and then each x and y is broken further in s and t. So we have, this is the tree. And this is how I learned the branching, because z and then depends on two variables. So z depends on two variables, and then x depends on two different variables. X depends on two different variables, and then y depends on two different variables. Depends on two different variables. Okay? So making the tree, if x depended only, let's say x was equal to t, then you will just have x and then t, and no s. All right? On this branch. And then the other one might be s plus t. You have both. So the branching is done per function per level. So z is the top level and branches into x and y because there are x and y that impact z. And then x alone is again s and t, and y is x and t. So now that we have this, we can write our partial chain rule, partial derivatives. So we have partial z in respect to s. We follow the branch that will take us from z into s. Remember that every time when we have branching is a partial derivative. So z branched, so dz dx times dx ds plus dz dy dy ds. They're all partials because I was branching all over the place. So now to plug in everything, dz dx is just e to the x plus y times dx ds is t plus e to the x plus y times dy is going to be 1. So now you can factor out e to the x plus y in parentheses t plus 1, and you can plug in what x and y are, which is e to the st plus s plus t times t plus 1, because we want everything in terms of s and t. Make sure she doesn't fall down the stairs. Okay, so that was a partial derivative of z in respect to s. Now we're going to find the partial derivative of z in respect to t, which is partial derivative of z. It's the other branches that we don't have, partial x, partial t, plus partial z, partial y, partial t. There we go. So we have e to the x plus y times s in this case, plus e x plus y times 1. So the answer is exactly this. The answer is symmetrical. Done. Yes. Tangent plane problem. So what was the section, sorry? 12.7. Problem number 19. Z is e to the xy. Is that one?
Yep.
So z is equal to e to the xy. We are looking at find the tangent plane. So find two tangent planes at 1, 0, 1 and 0, 1, 1. The tangent plane, we find the tangent plane when we find the partial derivatives. So we find the gradient first. That's going to be so what's the partial derivative of actually, sorry, let's first write the function in a form. So f of xy is going to be e to the xy minus z, minus z equals to 0. So now del f xy z so what do we have? Partial derivative in respect to x is e to the xy times y. Partial derivative in respect to y is x e to the xy, and then negative 1. So now to find our vector, if you remember for planes, it was vector v, right? Vector v was when you plug in the numbers. So we do at 1, 0, 1 point, So plug in y is equal to 0, that kills it. Plug in x equals 1, and then you have negative 1. There we go. All good? Yeah, y 0. So e to the 0 all the time. It's 1. You can't dot the vector on a point. You find the gradient and you compute the gradient. Once you have the gradient, then we are going to just write the equation of the... Oh, why did I put a vector v? That's for lines. It's n. Gradients are perpendicular. Oh no, it's two problems here. Problem A, problem B. So now we're doing it at 1, 0, 1. So we just need to write out the equation now. Starting with 0 times x minus 1 plus 1 times y minus 0 minus 1 times z minus 1 equal to 0. So that's one dies. We just have y minus z is equal to 1. No, that's negative 1. And there it is, tangent plane, TP. And now you recompute this for the second point, 0, 1, 1. So we are doing two separate problems here. Compute the gradient at it again. So for the second point and 2, it's going to be plug in 0, so 1, 0, negative 1. And we plug everything into equation. So 1 times x minus 0 plus 0 times y minus 1. Well, that's going to cancel. And then we have negative 1 times z minus 1 equals to 0. That's going to be x. This one is gone. Minus z equals to, that's 1, negative 1. Another tangent plane. So they're asking us to find two separate tangent planes, right, at two different points. Good. What else? Yeah. All right, 29 for the limits.
Monday.
See you on Monday. Limits are 12.3. And we have 29, problem 29. It says limit as xy approaches to 0, 0 of y to the fourth minus 2x squared divided by y to the fourth plus x squared. We are supposed to find, you first plug in 0, you see it's 0 over 0, so this might be a candidate for limit does not exist. So now we are supposed to find two different paths that will give us the different limits. If two different paths give us different limits, that means the limit does not exist.
You know how when you like you copy this one, you do limits, and if the powers are the same, then you can just take one. If the highest powers are the same, you can just take from one. Since these both are the same for both of them, you can just take that.
Nope. If you were thinking about L'Hopital's rule, because it's 0 over 0, two different paths. So the test question is either going to be a limit where you plug in and you get number 7, and the limit is 7, right? Or it's going to be something where you find two paths. So you can say, you can start with y equals mx, plug that in, and see if you end up with something that depends on m. If you do, that means infinitely many paths, because the value of the limit depends on which m you pick. That means the limit does not exist. So we plug this in. When y is equal to mx, then you only have x value left. So limit x goes to 0. And then y equal mx, so that's going to be m to the 4th, x to the 4th, minus 2x squared. I remember this. Did we do this in class and we got negative 2 every single time? I think it was this problem, right? We tried all of the polynomials and we tried exponential as well, and every time it would give us negative 2. Yeah, and we were suspecting that that was the limit, actually. Yeah, I think it was this problem. Yeah. You just flip the notes to the problem. It was this one. Yep. Raphael found it. Yes. Any formula, any sine x. Y equals sine x is approach. Sine x, cosine x, e to the x, ln x, any function. You got one? All right, so this was done in class. Skip this. What do you have?
As xy approaches pi comma 0.
So limit xy goes to pi comma 0.
For tan xy plus cosine xy all over 4x.
Tan xy. Okay.
And then cosine xy
So tangent times cosine.
all over 4x.
4x, like this. Yep. So I'm sorry?
Sorry, there's a plus.
There's a plus. That will be good. Yeah. So now we are going to, guys, all you do is you first try to plug these points in. If you get a finite value on the end, that's the limit. If you don't get a number, then you look for paths to show that it does not exist. So when you plug in pi and 0, this one dies, this one becomes 1, and this is 4 pi, 1 over 4 pi. That's the limit. So this one is good. Wait, are you solving the quiz now?
No, I'm doing class prep. Or no,
Study plan. It's like, oh yeah, that was on the quiz. That's correct. Like, good. Fantastic. Moving along.
Thank you. Limit as xy goes to e to comma e to the 6.
xy happen what?
xy goes to 8, comma, this x for ln cube root of xy.
That's it.
Yeah, that's it.
We plug in again. So it's going to be just ln cube of 8e to the 6, which is equal to ln, and now we take the cube root, which is 2e squared, which breaks into ln 2 plus ln e squared, which is ln 2 plus 2 ln e, which is 1, so 2 plus ln 2. So the limit is 2 plus ln 2. Fantastic. Apparently I know this. It's magic, man. Tu am?
So the limit, we put this, we put the variable in if it doesn't work, and then we have to do
The paths. Y equal mx. You start with that, yeah.
and if the y mx doesn't work, we have to do the y equal to m
X squared.
one more method, right? Differential equation.
Differential equation?
Yeah, one more, and then linear algebra. Assuming we couldn't plug it in, can you give an example of two different paths we could set up y to be equal to?
Y equal x squared.
Y equals what?
X
No, y equals x squared. That's
x squared.
Oh, I didn't know it was that equal to.
Anything else?
Number 27 on page 926.
Oh, I had a very important. So what was the page?
Section 12.6, number 27.
12.6, number 27. Problem 27. Directional derivative. (12.6), problem 27. So we have fxy given as x squared minus 4y squared minus 9, and we have a point P 1, negative 2. They want to find the unit vectors that give the direction of the steepest ascent and the steepest descent. Find a vector that points the direction of no change in the function at P. What now?
We do fx and y function.
Yes, we find the gradient. Good. So gradient f is equal to 2x comma negative 8y. Then what?
Now you got to solve it at point 1, 2.
Okay. So we solve this one at 1, negative 2, and we get 2 and 16. Now what?
but that is the y equals mx plus b. Right?
Why?
You need to find a unit vector.
We need to find the unit vector.
In the direction of what the magnet is over.
And if it doesn't equal 1, you make it equal.
$256, $260. And then good. So this is the direction of the steepest ascent. And the descent is what? Negative of the same thing.
What is that point that you actually did?
At every point, so if you have here, you're looking at this shape here. The point could be here, could be here, could be here, could be here, somewhere. For this point here, the steepest ascent, straight up, straight down, point over here, right? But if you have irregular shape, it could go in any direction, right? So the point actually says this is the location at which you will be looking because the shape would be.
You actually don't have to incorporate that.
I did.
Oh, wait.
I understand 10 to 10, right? And you work.
Now, in unit, you already had a unit vector.
I'm sorry?
You already had a unit vector above with dotted with evaluated at one number, right?
No, because that is the direction derivative. They are not asking the direction derivative. This is just to figure out the directional derivative. Directional derivative is in the same lecture just before. You do get they say find the derivative in the directional, and then they give you the vector cross. You do the gradient. You do the gradient, and you got it with that unit vector they gave you. If they gave you a regular vector, you just take the unit out of it, and then you got it. If the test is tonight, I would know. But the test is not tonight, so the test will not be done until.
It's freaking hard. Like, you don't know how nervous he has been, like, this whole week.
Few months, so much for a guy from SpaceX launch team.
Kyle.
See, there you go.
How do you just say gazebo?
My great grandmother was born in Mexico, so Mexico.
So it just stays.
Now I'm at the top of the bell curve. That's where they're at now. And then I got you back. You know he's in charge. Don't mind.
Oh my God. No, I can't even think of this like yeah, a lot.
Is there 6 or 5 left? Oh yeah, so I think we got to do more. Is the fifth lab?
All right, guys.
Fifth lab extra credit or?